First off, Matteo, thank you so much for joining our knowledge sharing group today. So Matteo will be going through his work on BenchMARL, and also, as you guys heard, kind of TorchRL, and a bit of discussion around that. So yeah, really looking forward to this. Thanks a lot, and yeah, take it away.
Thank you so much. Yeah, so thank you very much for having me. It's a very exciting opportunity to share this project that we've been working on in the summer. This is some work that I did this summer while I was an intern at PyTorch, and it's in collaboration with Vincent Moens, which was my manager and the maintainer of TorchRL, which might be here today to answer some questions with me at the end. And then, of course, it was under supervision of Amanda Prorok, which is my supervisor for my PhD at Cambridge. So today we will be seeing mainly three things that I wanted to touch upon. Since we have 45 minutes, you get the full view of things. So the three things I wanted to talk about is simulation, learning, and benchmarking, maybe. And so simulation, on the simulation side, I'm going to be briefly presenting the simulator that we worked on in our lab. It's a multi-robot simulators, which is vectorized, and it's a platform to create scenarios or use available ones to benchmark algorithms. Then I'll be speaking about TorchRL and what is this project in general, and how it can be used for multi-agent reinforcement learning. And then I will be speaking about BenchMARL, which is the kind of product released at the end of my internship. And it's basically a marl training library with a focus on reproducibility and standardization. Okay, and this is a little bit of the agenda. I will briefly talk about my research motivation and why I'm interested in this. Then I will talk about simulation in the VMS simulator. Then how TorchRL works and how TorchRL works for multi-agent systems. And then I will talk about BenchMARL. And in the end, I have like 2 slides just on topics that relate to what InstaDeep is doing, on where we can have some discussions on the future of marl. But kicking off with the research motivation. So our group in Cambridge studies multi-robot systems and especially collective intelligence. So that is intelligence where when you put multiple individuals together, you achieve something that is greater than the sum of their parts. And this is something that we see in natural systems. And the question that our group tries to answer is how can we achieve it or improve it in robotic systems? And why do we look at multi-robot learning for this? Because there is a lot of research in this field. And one of the main motivations is because the centralized sequential decision-making can be extremely hard. And for example, on the right, you see an instance of a multi-robot path planning problem where like multiple agents have to go from their source to their destination while not colliding. And this problem is NP hard, and its complexity grows exponentially in the number of agents that are considered. So if we try to develop exact methods or use exact methods to solve this, we get optimal solution. But on the other hand, our complexity will scale exponentially in the number of agents. On the other hand, we can think of using meta-heuristics, which lack optimality guarantees, but have good computational complexity. Because basically we traverse the search space for a solution using these heuristic methods. And multi-agent reinforcement learning is kind of something that I see as a trade-off between these two, where we can approximate optimal solutions through a training process. And then once we train on an instance, we hope to generalize to bigger instances just by replicate the concept. For example, in the case of multi-robot path planning, you might train on a small instance of the problem with a few agents and then hopefully generalize to a bigger number of agents. And in our lab, we did some works regarding deploying multi-agent reinforcement learning trained agents in the real world. And for example, here we have a first example of a GNN policy that was trained in simulation and deployed in the real world without any fine-tuning. And basically, this shows how it's possible to deploy these GNN simulation policies and what are the challenges of communicating in the real world, because the communication is done all decentralized on the robots. And we can see that here, basically, we show how the robots can organize to traverse a passage just by sharing communication with no visual information. In this other example, we have like a traffic routing problem when multiple agents have to like give way to each other and organize in order to improve the throughput of the system. And this is another decentralized problem that is quite difficult to solve as you grow in the number of agents. And lastly, something that I look into my PhD is how diversity in learned policies affects resilience for the agents. And so I look, for example, this was an example of deployment where two agents have to give way to each other, like by learning different roles in the task. Yeah, so these were just some examples of things that we're interested into. And to get to this, like the first step for learning is always simulation, because it's a core step in all RL, as we know, and it needs to be scalable, it needs to be fast. So what we did in our lab is a few years ago, we focused on this vectorization paradigm that now is getting more and more attention. And we basically developed this simulator, which is a vectorized multi-agent simulator. And it's a physics engine 2D written in PyTorch. And it also comprises a set of challenging multi-robot scenarios. And to give some examples of scenarios that we have, currently we have around 28, and you can see some of the renderings here. Basically, they focus on robotics tasks like bio-inspired, like for example, flocking, or we have some high-level coordination like with football games, or some, let's say, exploration-exploitation trade-off kind of problems with this scenario, which involves sampling a latent field. And then there are others, as you can see, like that are inspired by some of the tasks you've seen in the real world before, or just by some like heterogeneity that needs to be developed, and so on. And like, for example, scenarios that require a lot of cooperation are, for example, the ones where the agents are linked by physical joints, where that make their motion constrained to each other, which makes it quite important to cooperate to solve the shared task. And so, with this simulator, like what we want to do is for people to easily create one of these. So creating one of these took us, for example, 1 hour. It doesn't take much. And it's quite simple because we want to abstract this complexity of like a real physics engine, for example, like Isaac, because we don't care about the low-level fidelity, but we care about the high-level decentralized decision problem. So we are able to abstract in the parts where we don't need high fidelity in order to achieve greater speed. And since it's done for robotics, I just have a few videos showing how we take these policies, train in this simulator, and put them in the real world. And this is a video of just a robot tracking a trajectory that is a circle. And here is a video that you showed before, where we train before in simulation on a twin copy of the task, and then we deploy on the real world on these holonomic robots. And I think I don't have to tell you, but I always have this slide anyway. So just what does it mean for vectorization? It means that basically we are able to scale the number of environments that we simulate using the single instruction multiple data paradigm of GPUs. And basically we don't increase in computational time as long as the environment, the batch fits on the GPU memory. So here you see a plot that compares the number of parallel environments to seconds. And of course, when we run on the GPU, we're able to scale to 30,000 environments without an increase in the cost of simulation. On the CPU, we also have some benefits because of the Torch kernels. And then this is just a normal version of the scenario in MPE, where we just use a for loop to just show that scales linearly. And yeah, we compare with MPE because VMAS has all the MPE scenarios which have been vectorized in PyTorch. And how it is important for a library to take advantage of this vectorization is quite key to us. So we know that Mava and TorchRel can do this, but for example, some old-style libraries like marl-eval still don't have full support for on-device training and simulation. And so like the passing between simulation and training takes like for loops in the number of environments, or moves the data from CPU to GPU, or basically has to go through some interfaces which basically make vectorization quite useless in those cases. And so we can see that in TorchRel, as we grow the number of parallel environments, of course, we're able to increase these frames per second that we achieve because of the fact that it's all done in Torch and it's all done on device in a vectorized way. And so getting to how TorchRel does this, and what is TorchRel?
Just before moving on, I'm just curious, how difficult or how easy was it to transfer training from VMAS to something like Isaac Gym, or to the real world scenarios you showed previously?
Like How is it difficult to deploy the policies?
Yeah, so like how really I guess what I'm trying to figure out is how much benefit are you guys able to get by like are you pre-training on the VMAS and then moving on, or are you just using it to like kind of flesh out ideas and speed up iteration and then start again in the real setting? I guess I'm trying to hone in on how much speed improvement you were getting from doing it first in VMAS and then moving to the real scenario.
Right. Yeah. So in robotics, there are a lot of simulators like Gazebo, and you can think of the Isaac or like physics engine that are very accurate. Those we didn't use because it's very difficult to achieve the speeds we want, like running those in a vectorized way. Training, of course, requires a lot of samples, so we needed something that is very sample efficient, something that's vectorized. So what we did for these kind of scenarios that I'm showing is that we train solely in VMAS, and we directly deploy on the real world without any fine tuning. So we don't collect any data from the real world, or we don't train anything on the robots. What we did is that after the training happens in simulation, we just have to go back and forth and do some iteration of tuning for hyperparameters in the physics of VMAS. So for example, we have models for drag and for friction. And so we have to just get those just right for the robots in the real world to match the behavior of the simulation. And but we did like that. Something that we're very interested in is like using VMAS for like this high level like behavior, and then like doing this like low level adaptation to those fine tuning of hyperparameters regarding the real world, doing that maybe on the robot through some real world data that we collect. That is something we're very interested in.
Awesome, thank you.
No problem. Okay, and so regarding the learning part, what can TorchRel offer? So TorchRel, for those who don't know what is the PyTorch's officially reinforcement learning and decision-making library. It is a PyTorch initiative, so it has the quality standards and the guarantee of maintenance of the PyTorch organization. It's also up to date with the constantly up to date with the latest PyTorch features. So that, like, for example, distributions, probability distribution, functorch, and all that stuff. It's modular and integrated. So what it offers is like standalone component that can be used independently, but you can also integrate them together with something that's called a TensorDict, which is our data carrier. It's the plans are to have this kind of TensorDict move to Torch core in the near future. And basically it allows to carry tensors in a dictionary structure, which is very good for RL because of the heterogeneity needs that we have with our data. Then it has a syntax which aims to be unsurprising to RL practitioners. The functionality focuses on breadth over depth, and this is like in order to be more appealing for the research community, so that you can customize different components for your research needs. It aims to have a core dependency that is PyTorch only, but it's of course compatible with many simulators, and we have wrappers for many environments like VMAS, but you guys may know Jumanji, for example, Brax, also those kind of JAX environments are compatible. I don't have specific, I don't know specifically the cost of converting from JAX to Torch right now, but it's definitely possible. So yeah. And regarding this, how TorchRel is structured, we have like here I have the 4 main components, which is environments, that is an interface, like they are vectorized by default. They have transforms and specs, which are basically data structure defining the domain of your data. But they operate over tensors instead of, like, for example, the normal traditional GIM spaces. Then we have data collection components, which basically are similar to the data loaders that you may be familiar with in PyTorch. And these have a lot of flexibility for synchronicity, asynchronicity, distribution, parallel option. And of course, you have a lot of freedom on devices where you want to put things on which device in order to achieve some distributed kind of training architectures. Then there are modules which are key-mapped Torch models. So now, instead of having just the normal input-output that are tensors, you can use TensorDict dictionaries to tell modules which keys should it read and which keys should it write. And this allows for better control over what's done in a neural network. And so they are also compatible with, like, for example, torch distributions, exploration strategies, and all the VMAS and PyTorch compatibility stuff that is similar to what's available in JAX. And also there are a lot of losses, which we have most of the state-of-the-art ones, and there is support for target natures and value estimators and so on. But the core component that allows all of this to communicate, and it's at the core of TorchRel, is this TensorDict. And basically, as you can see, is a structure that it's similar to a dictionary, but it has some tensor-like feature, like a batch size. And the batch size will define the leading shape for all the values in the dictionary. So here you can see that you can group together different values that share the same batch size as the TensorDict. And by grouping tensors in this way, basically, this allows for efficiency and modularity. So these components that we see need only to communicate through TensorDicts. So you need to think about what signatures there are or stuff like that. TensorDicts will just try to carry the data needed between this component with regards to communication. And so even sending and receiving this TensorDict is made easy because essentially you're doing a tensor sharing, and on CUDA and on GPU there are a lot of mechanisms for doing like efficient communication across components. Yeah, and so just to give an example of how VMAS would run in this vectorized way with TorchRel, we have this example for an on-policy training, let's say, where we collect basically interactions with VMAS and the policies in a vectorized fashion, and we construct a TensorDict which represents my rollout, and then the TensorDict is already on the same device because VMAS is sitting already on device, and you can keep it on the same device and then go to the training loop where you can have another loop where you optimize your RL loss that's desired, and you backpropagate through the neural network to then update the policies that are using the collector again to gather more experience. And this basically also allows for asynchronicity between the sampling and the training phase, and it's something similar. I've read a little bit about the pod racer architectures. I'm not super familiar with it, but this kind of asynchronicity and communication from components sitting on different accelerated device is done in this way. Yes, and so like this summer, what I focused on to start with was like to create a multi-agent reinforcement learning interface for the TorchRel library. And I just wanted to give a flavor of like kind of the challenges that we've taken into account when developing these. And for this, I want to talk a little bit about the heterogeneity of the multi-agent reinforcement learning ecosystem. And this is various because there are a lot of differences in information sharing. For example, agents might share the same rewards, the same states, the same done flags, the same state value estimations. These components can be per agent or per team. But also the marl paradigm can differ in cooperation, where basically depending on incentives and reward functions, you can have cooperative or non-cooperative scenarios. They can also have physical heterogeneity, where different agents have different observation spaces or action spaces, and so on. And so the data structure that you use will have to take that into account. They can have behavioral heterogeneity, where basically agents can be controlled by different neural networks or by maybe the same neural network but with different parameters. So there are a lot of paradigms there as well. And then there is a synchronicity where basically maybe not all the agents may have to step at the same time. Maybe it's a turn-based game, and so you have to account for this as well. And communication, which for us is very important, which is in some paradigms, agents before taking actions and after the observation, they may use a GNN layer for sharing some information and overcoming partial observability. So that's also something to be considered. And yeah, so you're kind of like you don't want to develop a solution which will basically prevent some of these applications because of how the ecosystem is so varied. We want to not overfit to one of these cases. And what we came up with is that some libraries rely on solutions that either stack the agent data together or have an entry for each agent. So for example, think about petting zoo. There are dictionaries where like each agent has an entry for its observation, let's say. But of course, in that case, you have a lot of flexibility when the data are different shapes or heterogeneous data, but you don't have vectorization over the agents, right? Because now you kind of have to do a for loop over this dictionary. And on the other hand, some libraries use directly stacking, where you can basically stack the agents together and basically have a new dimension which represents the number of agents, and thus you can vectorize and run operations over that dimension as well, and not only over the environment dimension, but also over the agent dimension. So each of these solutions has a benefit where stacking is more of a efficiency benefit, but different entries have like an heterogeneity benefit. So in TorchRel, we didn't want to overfit one of these solutions or to fix one, because there might be the one you need is dependent on your needs or your paradigm or your task constraints. And so we let you choose. And the idea behind this is that we have a grouping mechanism where you basically define agent groups, and agents in the same group will have their data stacked, and agents in different groups will have their data as different entries in the TensorDict. And by doing this, basically, you can benefit from vectorization as much as you want, depending on your heterogeneity needs. And what's very important is that once you have defined your agent groups and basically the structure of your TensorDict, then within an agent group, you can use any single agent component that's available in TorchRel, because we are just having one more batch dimension, and TorchRel is already agnostic of the batch size. So we can just reuse everything, and we don't have to redevelop, let's say, PPO or something like that if you want to use multi-agent PPO or independent PPO. And this is like the core of what we focused, because we didn't want to reinvent the wheel, basically, for multi-agent re-implement PPO, because it's already available for single agents. And so here I'm going to give, let's say, 3 examples of cases for the grouping mechanism. And this is a case where you have all agents in one group. As you can see, there is a group map for the group agents. And this it tells you that there is one group called agents, and there are 3 agents into this group. And if you look at the TensorDict, you can see the batch size B is shared among all these entries. But then you have an entry which is called agents, which is another TensorDict. It's nested inside the TensorDict. And basically, this one has a batch size which is B, comma, a number of agents. So it means that every tensor in this nested dictionary will have these leading dimensions. And so basically, reward will be different for each agent. You will have one for each agent, and done as well, and so on. With this paradigm, of course, you can even share reward and done. You just need to put it at one level out, not in the agent TensorDict. And so if you put it at one level out, you see that it doesn't have the number of agent dimensions. So in this case, the done will indicate that the done state is shared by all agents, and the reward is shared by all agents. Basically, you can see that all this data is stacked together, so we can just apply an operation to it, and it would be automatically run over the agents. And this is an example on the right of a VMAS scenario, which we train using this paradigm. On the other hand, you can think of grouping some agents together based on like behaviors, for example. So if you have like a football match between your agents, you can either think of group them based on the teams, or even like more fine, you can group them based on the behaviors. You know, attackers and defenders may have different observations, so you might want to keep those separate to be processed by different neural networks. And so here is an example. You can have 2 groups, like group 1 and group 2, and the batch size of group 2 will have B, comma, number of agents in group 2, and the batch size of group 1, again, B, comma, number of agents in group 1. And so everything you have inside this TensorDict, again, will be will have that dimension, and so on for each group. And if you want to share something, again, across the agents, you just need to put it outside. So for example, if you put the reward here, it means that it's shared by all groups. And you won't have it inside here. And this is a paradigm, for example, in simulators like ML agents, where agents are defined by behaviors, and in that case, you can group them by behaviors. And then, of course, there is like the naive thing to do, which is like, okay, I don't care about vectorization in the agent dimension. I just want to, let's say, have a different loss for each of my agent, or treat them very differently. So I can just have one group per agent, right? And basically, this allows you to be very flexible, but again, you might lose some benefit in terms of speed. And so here in this case, we have these 3 groups for 3 agents, where the batch size is just the data is just for one agent only in each group. And this is like something that is used in PettingZoo for their interface, or ErrorLib, for example. Okay, yeah. So, and lastly about TorchRel, here I just leave the details because we have some tutorials and we have some examples online on the TorchRel documentation. So if you're interested, this is a very detailed tutorial on how to train a scenario in VMAS using TorchRel, and here the scenario is basically navigating to a goal while avoiding collisions using a LiDAR sensor. Yeah. So if you have any question, I'm happy to answer them. Some questions about what I said now about TorchRel, or we can also discuss this at the end. Otherwise, I'll just move on to BenchMARL. Okay, just let me know, stop me if there are any questions. So BenchMARL, it's kind of the focus of today. So what is BenchMARL? BenchMARL is a multi-agent reinforcement learning library, which was created with the goals of reproducibility and benchmarking across different algorithms and environments. And there are some core tenets that we followed when designing this. First, and most importantly, reproducibility, because we want to enable the community to easier run and compare experiments. So this is done through systematic grounding and standardization of the configuration. We use Hydra, which is a Facebook package. We will discuss that in a bit. Then it has statistically strong evaluations, and you may be familiar with this because it uses marl-eval. And this is what provides that is that it's standardized and statistically strong plotting and reporting. So we leverage, basically, we stand on the shoulder of giants where people have already understood what do you need to report and how to report properly statistically significant results. And so we use that. And then it wants experiment independence, where it's designed to have components that are independent. So we have abstractions over algorithms, environments, and model choices, so that experiments will be agnostic of what specific algorithms or environment are you using, so that you can really just benchmark against anything that you want that's available in the library. Of course, being it compatible. If you want to learn like QMix on continuous actions, yeah, that's not available. But within reason, all that's allowable can be done. And we want it to be easy integrated. So as I said, we have these abstract interfaces over components. And so we have tutorials on how to create your own component to basically benchmark your own algorithm against what is available. And then the TorchRel backbone. So basically, we don't re-implement any RL components. We use TorchRel as our backbone, again, for the standardization goal. And this provides the performance and the benchmarks that have already been tested in TorchRel for the implementations of the algorithms, and also, yeah, state-of-the-art implementations. And why does it exist? This might be a problem that is quite familiar to this audience, because within machine learning domains, reinforcement learning has always been a little bit more fragmented with respect to shared community standards. And there was a reproducibility crisis, which was highlighted in the NeurIPS paper, in particular by marl-eval, where they did an analysis over, for example, SMAC and how fragmented the domain was. And they proposed some tools that also draw on some prior work from NeurIPS, from Reliable, from Google, where basically allow you to plot in a standardized way your benchmarking results. And while these papers provided the tools to plot, what BenchMARL tries to do is do the whole pipeline and basically go from one-line input where you ask what tasks and what environments and what algorithms or models you want, directly to those plotting tools to do it in a standardized way. And what is available in BenchMARL, it's basically, you can see on the algorithm side that we have some of the most popular, so the PPO-based losses, the DTPG-based losses. I've implemented a few new ones with our soft actor critic-based ones, basically Mazak and Isaac, which are basically the same concept as MEDPG and MAPPO. You just take the algorithm from the single agent domain, and you just use either a centralized critic or a decentralized critic, and you use the same kind of algorithm. And then there are some like discrete action algorithms, for example, like QMix, VDN, and so on. And for each of these, you can see what is the action compatibility, what kind of observability the critic has, if it's actor critic, policy of policy, or if you use probabilistic actors or not. With regards to models, for now we have an MLP, and models here are like a general framework which can be used in many contexts. So for example, if you have an MLP, this can be used in the context of a policy, but it also can be used in the context of a centralized critic or in the context of a a centralized critic with different shapes, the inputs. And we are working on currently also GNN and CNN models, so that basically you can mix and match. You can have an MPPO with an MLP with a GNN, let's say with a GNN actor, but an MLP critic, or both actor and critics are GNNs. And so like you can create new algorithms by mixing and matching your algorithm with the model. And then for tasks, we integrate, of course, VMAS, but then also some other ones that are like SMAC v2, which basically fixes some of the biggest SMAC problems, especially the one of the non-initializing the agents at random. And then there is also MP and some from petting to CISL. But we're really looking to integrate more vectorized tasks in this regard. And so all tasks are have like a standardized configuration and can be loaded. They are actually in AMSA, so you can also see what the available ones are. I heard a sound. Is there a question? Yeah.
Just a quick question. You say they're models MLP. Does that mean you only have? Do you have like recurrent systems? Like for example, in your IPPO, can you use recurrency or not?
Right now, no, but we are working on, like, for example, in Torch right now, we've introduced LSTMs and RNNs, so that's something we want to integrate. And basically, we have a model which is like a sequential model. So once we have other layers like RNNs, CNNs, and GNNs, you can even create models as a sequence. So you can do RNN plus MLP. That's what we aim to do, but for now, yeah, there is no recurrent models.
Cool, thank you.
No problem. Yeah, and so for running, you can see above some examples of just what you need to run, and you just need to define the algorithm, the task, and in the case of a benchmark, you just define a list of everything. So you want these algorithms in these environments, and basically Hydra multi-run, the engine will take care of running these pairs of experiments, and this backend that you can choose in Hydra, it can be either parallel or serial or SLARM. And just to give an example of how BenchMARL works, the input is basically this kind of, you can have also inputs from scripts, but like from the command line is where you see like the Hydra framework. And what you can do is like you define like seed, task, model, and algorithms. And here, as again, you can put a list of things. And basically, Hydra will decompose this in a set of experiments. In this case, you have 3 experiments. For example, you have IPPO with MLP on balance with seed 0, QMix MLP balance 0, MLDPG MLP balance 0. And so you have these 3 experiments. And for like here, we look into one experiment in particular. Hydra will load from YAML. All the configuration is stored in YAML files, and nothing is in Python. You will load from YAML the configuration for each algorithm and task that you require, and then load that into the experiments. And experiments, again, can be run in parallel, SLARM, sequential, depending on what you choose with Hydra. They are bring together into a benchmark, and then the data from the benchmark can be aggregated together with tools, and basically you can automatically get the output plots from the marl-eval project that will contain all the experiments that you run, and will basically merge them together into single reporting plots. And yeah, so for a deeper dive into the configuration infrastructure, yeah, we have this tree where basically we have algorithm folder, experiment folder, model folder, and task folder. And as you can see here, basically, this is what the configuration looks like. This is for the multi-agent soft actor critic algorithm. You have this YAML file, and this is loaded through Hydra. And what we do is that for each YAML file, we have a counterpart data class in Python, which basically is used to validate the domains of the data. Because of course, in YAML, you don't have type checking or type safety, and if you misspell something or something like that, that could be dangerous. So the data classes are used as schemas to load your YAML files. And basically, you can do this with Hydra easily by just specifying here some what class you want to use in Python. And this makes overriding quite powerful, because yeah, of course you can load the default configuration like this, but then it's at your fingertip what you want to change. So for example, here we have an experiment with the balance task, MAPO algorithm, and then you want to, let's say, change some parts of the experiment. You can just override these parameters here, like what device do you want to use, what learning rate. And the same is valid for the algorithm, where you can change, for example, the number of Q-value nets in the SAC algorithm, or you can change the target entropy, or you can change if you want to share parameters in the critic, in the actor. All those choices are available. And also in the model, as you can see here, it's how how you specify, for example, to use a sequential model. I know in this case actually no, but there is on the README basically it says how you can specify a sequential model, but here you just configure an MLP, and then yeah, for example, also the tasks can be configured, but for the tasks, it's kind of better. Like each version of BenchMARL is tied to certain YAML files which define the task, so that when you compare, you have to make sure that the same hyperparameters for the tasks and everything are the same, and that is done by basically binding them to a BenchMARL version. So when you point to a BenchMARL version, you have immediately access to the current state of hyperparameters in that version. And expanding a little bit on the reporting side, on the integration with marl-eval, you can see how when you run a benchmark here, you have all these components, and this in the middle is the format that is used for marl-eval to plot the results. And you can see it's basically a series of nested dictionaries, like one with environment names, one with task names, one with algorithm names, and one with seeds. And all the components that you run here will match to this dictionary. So for example, here we have 3 algorithms. It means that the algorithm dictionary will have 3 entries, one for each. Or if you have multiple tasks here, or multiple environments, or multiple seeds, this will be translated automatically in the dictionary. And so you just need to pass this dictionary to the marl plotting tool, and you can get the kind of plot that you're interested into from this. And one thing that I just want to note is that since we have this reproducibility goal, what we aim to do is to tune and publish basically environments on on all the algorithms available. So I just wanted to show you how we did this for VMAS. So we are publishing it, for example, on 1DB, and here we have like a general over all the environment reports for all the algorithms. As you can see, there are sample efficiency curves, aggregate scores, and then you can go into each of the tasks, and you can compare the plots plotted by marl-eval with an interactive 1DB plot, where you can like explore what went on and see the runs. And of course, you have access to the videos and so on, so you can really like inspect. It's like a CleanRL kind of thing where you can inspect interactively the plots of each benchmark that we publish. Yeah, and lastly, just a few features. So there is logging compatible with 1DB, restoring CSV, JSON, float, TensorBoard. There is checkpointing, callbacks. We have integration tests that run on each algorithm and on each environment, and they run in the CI, in the continuous integration in GitHub. And of course, one of the biggest features is the TorchRL backend, which means that everything will be maintained as part of the PyTorch RL project. So any update to the algorithms will be reflected in BenchMARL as well. Okay, and since it's already 2:40, I have just a few concluding slides on some discussion. And first, I wanted to discuss a little bit standardization in the field. So one thing that I think is important, like even if you don't, I know that some of you really use JAX, but for any library, I think it doesn't really matter what you have between this input-output. Like, of course, there are people prefer Torch or people prefer JAX. But I think one message that would be cool if the marl community would be able to unify on is standardizing these input-output structures. And where marl-eval already did a great job for the output, where basically we have this standardized formatting tool for reporting your experiments, I feel like we could do the same thing for the input structure, where basically we can use Hydra and have some standardized set of basically configurations that can be like the same across different libraries in order for people to have the freedom to switch between them. And this would help, for example, aligning performance. If we have this unified input-output, you will have to have the freedom to switch from JAX to Torch while maintaining hopefully the same returns. And of course, some may be more efficient than others. You might be able to run the same experiment in half the time, but you would still hope that with the same number of frames, the same algorithm would get the same result. And also it will help sharing hyperparameters where you don't have to like figure out how did they do it, but if you have this like Hydra structure that is shared, basically it will be much easier. And also uniform results reporting, and this is basically where marl-eval and Reliable focused on which is a really important part of it. And lastly, some discussion on Torch versus JAX. I just want to say that this is my own opinion. It doesn't reflect the opinion of anyone else. I just put together some things that I thought. But basically, I just wanted to break down what's available right now in JAX and Torch with regards to 3 dimensions, like compilation, vectorization, and distribution. As we know, compilation, like one of the best features of JAX is JITting, just-in-time compilation, which compiles the code at runtime. And Torch has been working for a while on torch.compile, which basically does the same thing with a different backend. So JIT uses XLA compiled code, while torch.compile uses Inductor, which is a mixture of Triton and C++. But basically, one thing that Torch does in this case is that if you have functions like this one, basically in JAX, this Python control flow, it's actually has to be avoided as much as you can because of the tracing mechanism. While in Torch, a function like this will be automatically compiled into three parts of a graph. And every time the control flow instruction is encountered, the graph is bifurcated. And so basically, you can have custom Python code within a compiled Torch function. Then with respect to vectorization, some things that people love a lot about JAX are VMAP, GRAD, and JVP, because they're very efficient. And Torch has recently introduced the counterparts of these, which also we make heavy use of in TorchRel. For example, the VMAP functionality for where you have ensemble models that is very useful, or even when you have multi-agent systems, right? Because you can just VMAP over the agents with different parameters. And there is also like this functional call, which allows you to run a traditional Torch model in a functional way. And then regarding distribution, I was looking at, like for this talk, I was looking at these pod racer architectures for TPU pods. And basically that they leverage also a lot of PMAP, which is a very cool JAX feature. And I was just trying to think about the equivalence in the Torch domain, and in this case, the Torch distributed has some equivalence of PMAP, and there is also a team at Torch working on XLA support, so basically on how to run Torch code on TPUs. But with respect to regards to like the specific architecture, I tried to like make a little bit of a mapping between environments collector. And so in TorchRel, you have these components. For example, environments can be multi-process, can be vectorized. Collectors are the same, and they can be vectorized, multi-process, and also distributed. And then losses also. So a similar paradigm where if I get like the core idea behind this, it's like that you leverage basically low latency communication in a TPU pod, and basically asynchronicity between the different components, where you have like a cores that only dedicate itself to collecting and cores that only dedicate themselves to training. You can kind of try to have this kind of distribution in something like TorchRel with asynchronous collection and training that can be done on different devices with CUDA communication layers for the background. Yeah, and this is kind of all that I wanted to say today. If you want to reach out, feel free to write to me. I left some link to the repositories. And thank you very much.
Hey, Matteo. I have a quick question. So I know that you like separated the kind of BenchMARL pipeline into input, kind of processing, output. How intrinsically tied to I mean, I know you say it's like the TorchRel, the backbone, and it's a very important feature, but would it be simple to essentially swap out TorchRel for something like, or even like a Suborbital type kind of pod racer architecture where you just kind of output data in some format for BenchMARL to collect? You know, like how easy would it be to do something like that?
Right. So on the output kind of front, what we do is basically to be able to generate results. This output is the JSON file that then are read by the marl-eval project. So in that case, I think any library that produces files in those formats can be used, right? As long as, like, of course, the implementations, like the number of steps mean the same thing and so on. But assuming that's the case, you just need to like adhere to the marl-eval format. With regards to the input, Well, so we have this kind of hierarchical configuration with Hydra, where we have like a folder for the algorithm and so on. It really depends on what kind of framework, because if it's already being developed with different Hydra configuration architectures, I guess that would be needed to be changed. But of this kind of thing, I would say nothing is dependent on how it's actually implemented in BenchMARL. Essentially, what you want to do is tell it what task, what environment, what model, what algorithm you want. So as long as these kind of configurations can be run in another library, like for example in Mava, you can run this environment with this model with this algorithm. I would think that it's possible. There might be some initial lifting on the configuration side, but then yeah, it doesn't really if you use a different type of backend, you should be able to. It's just a matter of the interface, in my opinion.
So if I cloned BenchMARL and I created my own run file and I used your logger, then it would all relatively pipe through, in theory, perfectly.
Yeah. If you use the logger that writes the JSON file according to the format that it's needed, you just need to provide it the data it needs, right? So you can get that data as you want. With regards to the configuration, you can take example of how the architecture of the YAML folder is, and try to have a similar architecture in your own project. It seems doable to me. I don't know how much code from BenchMARL would you use, but it's essentially to take inspiration from the same configuration architecture. It should be really simple. If you're already using Hydra, it's even simpler.
And the automatic 1DB reporting, is that all done in the output formatting of BenchMARL? Like after you produce the JSON files and you get the plots to kind of produce an automatic report and do 1DB logging, is that also just a separate logger, or is it a separate kind of process?
It's a separate one, yeah. So basically, the logging and the reporting are running in separate classes. So there is one class that just cares about the JSON reporting. And then for the logger side, you can choose multiple loggers and mix and match them. So in that case, that's what handles 1DB or CSV, and you can have multiple at the same time. Those classes, the logger classes, are kind of BenchMARL specific right now. So I wouldn't say that they're ready to be brought to another library, because we have certain conventions for how keys that we want to report our code, and of course they use TensorDix to read those keys. But for example, for the JSON logger, that's a much more flexible interface where it takes NumPy arrays. So so probably we would be able to recycle the JSON logger, but the main loggers, no.
Okay, thank you.
No problem.
Hey Matteo, first of all, thanks so much for a really nice talk. Really enjoyed it. Interesting work. So I have quite a few questions. The first one stretches a bit back to the training and simulation, and then porting that to the robots you have in the lab. I'd be interested how the action space mapping works, because I can imagine it's sort of some simple discrete actions within the or it might be continuous within the simulation, but then when you go to the actual robot, I can imagine it's somewhat more complicated. Or is it just you can tell the robot go forward, left, right, that kind of thing?
Right, so we had to do some adaptation there. Basically, our simulator is force-based, so the inputs that we use to control the robots are forces and torque in 2D space. In this case, our real-world platform had velocity controllers, so basically it would take velocity commands as input. So what we did there is that we developed an action pre-processing layer for VMAS, so that basically in order to make our neural network output velocities, and then we just have a PID controller which converts those into forces for the VMAS simulator. But with regards into the action domain itself, in this case, the robot is holonomic, so it's fine with getting an input action which is a 2D velocity. It's just constrained in the domain, but let's say -1 + 1 meters per second, and you just need to match that in the simulator, and that works.
Okay. Cool. Then the other question is more sort of, I guess, a bit high level philosophical question. So let's say journey with developing Mava and developing like general tooling and things for multi-agent RL, we've gone from like one extreme of very extreme kind of flexibility support through really complex callbacks and hooks and things, and tried to be as modular as possible. And there seems to be a trend now, with libraries like CleanRL and things where it's sort of single file, and that's where we're leaning more these days. And I'd be interested to get your opinion on how you see that. What do you think is sort of a good trade-off? And what is your experience with something like TorchRL being quite modular, and it seems like you guys really want to support this flexibility of swapping out different network types or different things within the same algorithm just to make it easy to implement new things. Do you think that sort of level of complexity, you get return on investment on that through being able to just quickly implement things, and the maintainability? If you have thoughts on that.
Okay, yeah, thank you very much. This is a great question. And if Vincent is in the audience, maybe I will also pass the ball to him, since he designed TorchRL this way. I can give a shot at it, and then if he's here, I'll pass the ball to him. But yeah, so that's also something that we faced when we start designing BenchMARL. Like I saw that there was this one script trend for like CleanRL. But the idea is, it's kind of like, what is the product that you want to provide? Like, and also what's the audience? Like, what do you imagine the community will use this for? In the case of BenchMARL, basically, we wanted a tool that makes it as simple as possible to basically mix and match different algorithms. So for that, since we have to like compare different algorithms, if we had single file implementation for each, because at that point you might have like single file implementation for each pairing of algorithm with environments, right? Maybe QMix in SMAC, and then QMix in VMAS, and so on. And like when you change from discrete and continuous spaces, maybe you want 2 files. And so at that point, it seems like the benefits of the readability, because of course these kind of things are very understandable. Like what people love from CleanRL is that you can just go in, read one file, and get familiar with that algorithm, right? And if you are trying to unpack something like more complex and more object-oriented, of course you might have to go through chaining of inheritance, and that can get some complex. But for the scope of BenchMARL, we kind of knew that the path we were going to take. So for that, it was kind of like a no-brainer. When it comes to TorchRL, I don't know, Vincent, are you here? Do you want to speak about how TorchRL? Okay, I guess maybe he's not here. So I can say a few things. Basically, TorchRL, what it aims is not to provide the library something like stable baselines or something like errorlib, where you have like end-to-end all something that it's like a blob that it's very difficult to disentangle. But also it doesn't want to provide single file implementations because the current aim is to be in the backend, to act as a backend for existing Torch reinforcement learning libraries. So one of the hopes is like something like a stable baseline would integrate and use TensorDict as part of the backend. So by providing these isolated yet integratable components, it tackles sub-problems of RHEL. So, for example, I saw that you guys just released like a replay buffer class, which can be used independently. And the same thing goes for TorchRL. You can take the replay buffer and just use that in, for example, in your single file implementation script. So if you want to build like something like CleanRL, and then what kind of libraries would you use in your single script? So there the decision was like on tackling this type of audience, the type of audience that would use components from TorchRL in their own implementation. And so for that, there needs quite a lot of coding, for example, like compatibility with the PyTorch world and PyTorch ecosystem. And also just in general, like PyTorch has always taken this idea of providing classes that are like this. But I do see the value in one file implementations, especially the readability value, and I think that's that's one of the things that you kind of miss out when you go to these more complex and object-oriented projects. Does that answer a bit the question?
Yeah, no, thanks so much. I have so many questions, so maybe I should just pick the ones that I think are most important. You mentioned the difference, sort of compatibility or mapping between PyTorch and JAX, and PyTorch now has the compile. Whereas JAX compiles the XOA, you said PyTorch has something else that it compiles to.
Mm-hmm.
I mean, it's really nice and impressive that the control flow is not such a big deal, and peer functions might not be really necessary. But do you have some sense of speed comparisons when you if you were to use the same function and compile it to,
Yeah, that's a super interesting question. I've been looking for, when I was preparing this presentation, I was looking for that, and I wasn't able to find it. I think we do need something like this, but so basically, overall, it depends, right? Because it depends on where you implement it and what backend do you use. For example, torch.compile has different backends for different use cases. The one I talked about here is Inductor, but there is others that trade off overhead for efficiency. In general, JITting is something that JAX is really great at. So Torch is trying now to get the benefits that you have in JAX. I don't think there are public ones released by PyTorch, also because it's quite a new feature. It's evolving very rapidly, and this compile thing just came out very recently, and it's also evolving at a pace. So we will see constantly new iterations of it. I'm also interested in that, and I don't have that right now. But we definitely need some of that, especially when people are choosing what library. Now there is a lot of people that approach RHEL and they have to choose, and so improving something like the slide I have here with actual data, it's definitely something important. And yeah.
Okay. No, cool. And maybe last question. Again, a bit more philosophical, but when developing these frameworks and libraries and things, I guess maybe it might be different from the PyTorch side of things because of its scope and its adoption. But when you think about developing things, do you almost think community first? What are the problems that you could hypothetically foresee community members would care about and we would like to solve them? Or is it more what do we need for our research? What do we want and want to drive forward to solve our own problems? Because when we develop things, we kind of go between the one and the other, and we're not entirely sure. Sometimes we've been trying to solve problems that aren't really problems that we ultimately care about and should be solving. We're leaning more towards developing for, I don't know, in-house needs, and if it's useful outside, then that's cool.
Yeah, that's also a great question. I can speak for myself and my experience. I don't know about the whole Torch team, but when it comes to myself, it's always a balance between the two. The first approach, especially the first community project that I did, was the VMAS simulator, and it came from an in-house need. We needed something for training our robots, and what was out there was simply not doing it. It was either not vectorized or not at the level of complexity we wanted. For example, we tried experiment with Brax, but the overhead was huge, and we needed way simpler physics than what was provided. And so at that point, once you realize that you have the need for it, then I guess we ask the question how many people would benefit from it? And so if we are going for a community project, then at that point, we try to extend it as to support features that are also not needed in-house. Of course, I mean, you can go infinite like this and satisfy everyone's requests, and that's unfeasible. So it's still a balance. But when it came to the BenchMARL projects, I was really inspired by the work that was done at InstaDeep with that was a very community-driven project, right? You guys collected the database and then did a lot of tooling that would help for plotting. And so at that point, when it comes to benchmarking, seeing the state of the community and every paper comes out that still uses Mac, I feel there was a greater need for something that is standardized. So I don't like aim to fix this with BenchMARL, of course, but like just starting to go in a direction where like reproducibility becomes one of the first focuses, even if you're doing something in-house, because like in the long term that can help. So yeah, I mean, it's a balance of the two, and it was more for the community when it comes to BenchMARL, more for in-house needs for VMAs, but yeah, in general, it's always a balance.
Okay, thanks so much. Yeah, sorry for hogging the mic. Thanks again for the presentation. And regarding standardizing the input side of things, yeah, fully in support of that. So if you have ideas, please feel free to reach out.
Yeah, thank you very much for all the questions. And yeah, definitely we can chat on that. If I don't know what's the current scope of Mava, but or if you use Hydra, but we can definitely chat on those things.
Yeah, we do use Hydra. Yeah, and actually, Ron, I don't know if you want to speak a bit about like also JSON logging and things that we've really appreciated from your side. Yeah, sure.
Yeah, I can. Like Arne mentioned, we're using Hydra already, and then really so nice to see that marl-eval is being used. And that it's appreciated. It's very encouraging to see. And then also your JSON logger is amazing. We're actually in the process of adapting your JSON logger to use it in Mava ourselves. So super, super nice. Thanks for that.
Yeah. Yeah, feel free to CC me on if you or any pull requests. I can help and stuff.
Amazing. Thanks so much.
Cool. All right, we are a little over time. Any other questions people have before we wrap up? Okay. Well, in that case, Matteo, thank you so much for joining us today. It was a great talk, a huge amount of interest from our side, very valuable, and yeah, hopefully we can all stay in touch. Thanks everyone for joining today, and from our guests joining outside of InstaDeep as well. And then last thing, for anyone that wants to propose a knowledge sharing talk, please reach out. We're very keen to get more of these up and running, both for internal projects and also external speakers. It'd be great. All right. Thanks a lot, guys. Cheers.
Thanks, Matteo.
Thank you so much for hosting.
Thank you.
Yeah.
Thank you.
Thanks.
Thanks.